download system. Okay, it's now 3 minutes past 9, so I believe that we can start the third lecture. So the topic of the lecture is performance modeling. Before moving on to the actual material, I have to mention this remark, which is that usually when you are trying to measure, for example, the execution time or the throughput rate or the memory bandwidth, you should strive to measure everything multiple times and then go and compute averages and variances and apply some sort of statistical methods to make sure that the results you are getting are statistically sound. But in this course, we will be measuring things only once. And the reason behind is that when I was looking at the number of participants registering, we had 50 people and we managed to acquire 6 GPUs. So I got worried that if we have many people running longer jobs where they're averaging the measurements over, let's say, 10 to 50 runs, that would end up filling the GPUs entirely. So during the hands-ons, we will just do one measurement in general. Of course, you can repeat it if you feel that there is something weird with the number, but otherwise, I'll be assuming that we are measuring only once and then hoping that the result is not a huge outlier. So performance, how do we measure it? Usually when we want to tell people how powerful a CPU or GPU is, we will talk about the flop rate. And flop rate is simply defined by the number of floating point operations that are being executed divided by the time how long it took to execute those operations. And this gives us a flop per second, or flops in short. Usually what is counted here are the number of floating point additions and multiplications. And this is because modern hardware can execute these operations very fast. There is actually a separate instruction called FMA, fuse multiply addition, that will actually do both one addition and multiplication during the same cycle. If, on the other hand, we put like divisions or some trigonometric functions here, then you would usually get a much lower flop rate, because the modern hardware, even though are very powerful with FMA instructions, in relative terms, they are far less powerful when they are doing, let's say, floating point or integer divisions. So let's go back to these figures I showed you yesterday morning and look at the theoretical peak flop rates that can be calculated for each device. And for this quad-core desktop CPU, you get around 200 gigaflops. And for the 14-core Xeon, you get the 1200. And for the NVIDIA V100, you got the 7 teraflops of computing power. So if you just look at these numbers, you might conclude that the V100 is around 11 times faster than the 14-core Xeon CPU. And of course, if we are willing to reduce the precision, then the difference will be even larger, because on the CPUs, when you go from double precision to single precision, you more or less double the performance. But on a GPU, V100, if you're willing to go to half precision, then you will get this theoretical figure of 112 teraflops of computing power. So in that, if you're interested in doing something that only requires half precision, let's say some AI applications, then V100 would be on the paper 90 times faster than the 14-core Intel Xeon CPU. So let's do a couple of experiments. First, I'm going back to this simple example where we are multiplying a vector with a scalar. And assuming that the vector length is n, then we will do, yes, I'm recording. The total number of flops that we are performing is going to be n, because there is one multiplication for each element in the vector. I'm hearing some from echo in the recording. Okay, does one of you has a microphone enabled? No. Okay, I don't know what it is then. Yes, so total number of flops you are executing here is going to be n, and the total number of bytes that being transferred is going to be 16. So we have to load the element which is going to be a double precision number, 8 bytes, and we have to store at the end is going to be 8 bytes, a total of 16, and flops, bytes are being moved to and from the memory. And again, looking at the CPU code, we have for loop here that simply iterates over the length of the array, and then I parallelize it with the OpenMP parallel for. That will basically going to split this for loop into chunks and assign these chunks to the set of threads that will do this multiplications parallel. And yesterday you saw that the kernel for the GPU would look something very similar. but there we actually have a lot more threads, and then in most cases each threads end up doing just a few multiplications. And then I went to run this code that can be actually found from the hands-ons directory. And for the quad-core desktop CPU, we know that if we do, let's set the N to be 500 million, then the runtime is going to be around 292 milliseconds. For the quad-core, the Intel CPU, if we run it with the 14 threads, the runtime is around 88 milliseconds. And for the V100, the runtime is around 11 milliseconds. And when we go and crunch the numbers, we know that V100 is around 8 times faster than the Xeon, which is reasonably close to the 11 times faster, theoretical 11 times faster figure that I showed you earlier. But if we actually go and compute the flop rate, we know that with this Skylake CPU, we got only 2 gigaflops out of the 200. And with the 14-core Xeon, we got 6 gigaflops, which is out of 1200. And V100, we are getting 47 gigaflops out of 7000. So we are being faster, but it seems that we are using only a very small fraction of the theoretical flops that can be executed in a second. So it's 8 times faster, but across all 3 platforms, we are using only 1% of the theoretical flop rate. And now the question is, why is this happening? What else could be affecting the performance in such a manner? So the second thing people consider is the memory performance, which is measured in terms of the memory throughput. And there we take the number of bytes we have been moving and dividing with the time how long it took to move those bytes in the memory. And usually this measurement is performed between the CPU cores of the main memory or the CUDA cores and the global memory that is placed on the GPU itself. And again, you can either calculate this theoretical memory bandwidth or get it from the manufacturer. These are just rough numbers. For the desktop CPU, it's around 35 gigabytes per second. For the Xeon, it's around 100, and what NVIDIA is promising for V100 is 900 gigabytes per second, which is almost a factor of 10 difference. And when we now go run the same code, and in addition to computing only to the flop rate, we also go with the memory throughput. And this time we can see that we are actually getting 27 gigabytes per second out of 35, 95 out of 100, and 756 gigabytes per second out of 900. And here we can see that we are actually using between 77 and 91% of the memory bandwidth. And then if we use some profiling tools, NVIDIA provides this tool called NV Nsight-Q command CLI. And the CLI here stands for command line. You can also launch this application without the CLI addition, and it will actually open a graphical interface that is much more friendly to use than this command line version. But since we are using the GPUs here through a command line, I have decided to show you how it looks like if you run it through the command line tool. And it's very simple. You just submit the jobs as before, but then you just put the NV Nsight-Q CLI and then put the command you want to run and the arguments that belong to that command that you're running. And the output from this command is quite long. So what I'm showing here is only a subset what is to be shown. But at the very beginning, you have these fields, which is called the speed of light analysis. And from here, we can pick 3 key rows that tell us about the performance of the code. And the first one called Sol FP. Sol stands for speed of light, and I'm not entirely sure what the FP stands for, but based on the documentation, it's related to the global memory throughput of the kernel. And memory is then related to the occupancy rate of the memory subsystem. So based on how NVIDIA has documented this, it looks like if Sol FP is very high, it's telling you that you have very good code in terms of how much memory it can use, how much memory bandwidth it can use. And the memory then tells you how active the memory subsystems such as memory controllers are. Because as I mentioned yesterday, you can write your code in a manner where you're pulling way too much data from the memory. And in that case, you would have this memory being very high, but Sol FP would be really low because you are not using a lot of the data that's being pulled by the memory controller. Then we have SM, and this is related to occupancy rate of the computing resources. And what we can conclude here is that clearly this ASM is very low. It's only 3.34%, which indicates that the CUDA cores are being idle, whereas the memory system is being reasonably busy and clearly moving data around the memory at a reasonable rate. Well, let's look at the second example, which is slightly more complicated. Here we are given two matrices, so two two-dimensional arrays full of double precision numbers, and we are simply going to multiply them together to get a third matrix. A naive implementation, and I would emphasize this word naive here, is that we simply have a three nested for loops, and inside the innermost loop we will do, for each element we will do multiplication and addition, and then we will store the data back to the memory. And when you count the number of flops, we have two flops inside three nested loops that all loop over n iterations. It's going to be 2 times n squared number of flops. And total bytes being transferred, inside here we have to load 2 doubles, so it's going to be 16 n squared, and then we have to store 1 double back to the memory in the this inside the 2 nested loops. And I must emphasize that this figure is okay, but this figure it's not actually realistic. And during the close to the end of the presentation, I'm attempting to explain to you why this figure cannot be trusted when you actually measure the memory bandwidth when you are using a modern BLAS library to actually doing this operation. If you would implement this yourself, then this figure would be accurate, but the high performance libraries implement this code very differently, what I'm showing here. So I ran the similar comparison. I'm pointing out that here I'm using an optimized BLAS library. So I'm not using this code, I'm calling a routine in the open BLAS library. And again, I'm running this code, and I'm using a four threads on the quad-core desktop CPU for matrix size of 5,000 times 5,000. The runtime is about 1.5 seconds, and the flop rate is 176 gigaflops per second out of 200, which sounds now really good. And when I go down, again, I'm running with the 14 cores. The runtime is about half a second, and I'm getting around 533 gigaflops per second out of 1,200. And for V100, the runtime is about 41 milliseconds, and I'm getting a bit over 6 teraflops of power out of the machine. I have added a footnote here regarding this number here, where everywhere else we are really close to theoretical maximum, but here we are actually close to being half of the theoretical maximum. And this is mainly due to the fact that for this course, I chose to use the Kufor's FOSS-CUDA module that loads a BLAS library called OpenBLAS. And this library is not as optimized for the Skylake CPUs. So if you had used previous generation Broadwell CPUs, you would get a very close to theoretical peak that is around 600. But with the Skylake, they introduced additional instructions called AVX512. And it seems that this library is not very optimized. So for this type of software, the theoretical peak is actually going to be around 600. So it is still very close to the theoretical maximum in the sense that it is not actually using the full instruction set to do the operations. So we are using somewhere between 46 and 88% of the peak flop rate when we are doing matrix multiplication. And again, we can look at the profiler. Again, it's going to print us a lot of lines, but we only care about these 3 here. And this time the memory system seems to be somewhat busy. It's not idle, but it's not even at the half occupancy rate. But the CUDA cores are clearly working at over 98%. So clearly for this code, for the reason, the CUDA cores are working really hard to do the necessary computations to perform the matrix multiplication. So these 2 codes end up behaving very differently. And now the next question is that can we somehow predict this behavior before we actually go and implement the code, run it, and then run it through a profiler to get to know what type of code we are working with. So I'm going to be introducing these 2 terms here without actually defining them that clearly. I'm calling this former type of code, this AX, as a memory bound, because based on the profiler and the results I got, it is clearly the performance is clearly being limited by the amount of memory bandwidth we have available. And the other type, this gem kernel, I'm calling it compute bound, because there clearly the performance is being limited by the number of flops the GPU or CPU is able to perform per second. Yeah, that is the performance of memory bound code is limited by the memory bandwidth, and the performance of the compute-about code is limited by the instruction throughput. And the first tool we need to do this kind of analysis is that we have to introduce a term called arithmetical intensity. And we define it by dividing the number of floating point operations with the number of bytes being moved from the memory. So the unit for arithmetical intensity is going to be flops per byte. And if we go and compute this arithmetical intensity for these two codes we just talked about, if we do a double precision, we will have one flop for each element in the vector, and then we move two double precision numbers. So the arithmetical intensity is going to 1/16 flops per byte. If we move to single precision, then of course we are moving half as much data. So the arithmetical intensity is going to be 1/8 flops per byte. And for a well-implemented double precision gem kernel, the arithmetical intensity is around 32. And this is a number I was scouting throughout the internet because it actually depends highly on how you implement the actual kernel. And in this instance, the average number I came up with a lot of searching was 32. And again, I'm going to be returning back to this number because at the end of the presentation explain how it actually can be that much higher compared to this AX kernel. And we can now go and plot a couple of algorithms. So here on the horizontal axis, I have different arithmetical intensities. And you can see that the gem kernel is here around 32. We have particle codes that are around somewhere on this range. And then we have deep neural networks that are here on the extreme end. Then if we move to the other end, we have a fast Fourier transformation, different kind of stencil code, sparse matrix filter multiplication, and then this XPA operation where you multiply a vector with other vector and add it to a second vector, and then here we would have the AX kernel. So clearly different codes that can have a very wide range of arithmetical intensities. And also please pay attention to the fact that the scale here is logarithmic, and that is for the reason, that is for a very good reason. And briefly going back to deep neural networks, I don't personally have that much experience with this topic, but I looked some numbers from NVIDIA, and they are telling you that when you're doing half precision computations using through the Cudidian library, then if your linear layer in a neural network that has around 4,000 outputs and 1,000 inputs, and you set the batch size, meaning that how many data points, let's say, you are processing in one batch when you are pushing to the GPU, then the arithmetical intensity they're promising to you is 350. In linear layer, that you simply make the batch size to be 1, so you're just doing inferential training with the one element at the 1, then you get the real low arithmetical intensity of 1. So clearly, changing the batch size will end up changing the arithmetical intensity. Then there were a couple of other, like max pooling in 3x3 window. I'm assuming that this is related to convolution operations. The ReLU activation function and layer normalization, these usually have a slightly lower arithmetical intensity, but it's still, even when you're doing, I'm assuming here that this is some sort of convolution operation, it's still 2.25. And when you remove the AX kernel, had only 1/16, so it's still quite high arithmetical intensity. So now I told you that you can compute this arithmetical intensity, and the next question is that what you can do with this number. And the math here is going to be a bit here and there. It is mainly meant to give you an overall idea what is happening, because the model that I end up telling you at the end, it's still considered to be more or less heuristic, but it can be surprisingly accurate. So if you want to know all the work we are doing in order to do the computations, that is going to be the number of floating point operations we are doing, plus the amount of data we have to move from the memory. And if we are assuming that all these flops and memory transfers are more or less evenly distributed through the code, then we can make a rough estimate that the total time it takes to run the code is the number of flops we have to compute divided by the number of flops the card device can perform per second, and or then it's the number of bytes we are moving divided by number of bytes the card can move per second, and we take the maximum number out of these two to give a rough estimate of the execution time for the execution time of the code. Since we know that performance for now is going to be divided by the number of flops we are performing divided by the amount of time it took to perform them, we can estimate the performance by dividing the flops with this earlier estimate for the time. And when you go and flop these numbers around, you will get following formula, which is that you take the minimum from the peak flop rate and this term where we have flops divided by transfers times the memory bandwidth of the card. And as you can see, what is here, this is the arithmetical intensity. So in order to get the estimated performance, you get a minimum out of the peak flop rate and the arithmetical intensity times the bandwidth of the device. So a very simple formula that you can use to estimate the performance. And for each device, you can now go and compute optimal arithmetical intensity, which is that you will take the theoretical peak flop rate and divide it with the theoretical memory bandwidth. So in case of V100, this would be 7,000 gigaflops, and this should be 900 gigabytes per second. And if you plug this optimal intensity into the formula here in place of the arithmetical intensity, you will note that these two guys cancel out, and you will simply get the peak flop rate. Meaning that if you have an algorithm that has arithmetical intensity that matches the optimal arithmetical intensity of the device, then you are expected to get the peak flop rate out of the device. And if you're in a situation where the arithmetical intensity of your code is smaller than the optimal intensity, then the code is going to memory bound, because then you are evaluating this side inside the minimum operation. So you put flop rate transfer to bandwidth, and that is always going to be smaller than the peak flop rate. And on the other side, you will have it where it's larger. In that case, the performance is going to be simply the peak flop rate. Yes, there's a question. Okay. Okay, I was asked to talk a bit slower, so I will just do a brief recap of what I said earlier. So we derived this formula that we can use to estimate the performance. And it is going to be minimum out of two terms. The first term is the peak flop rate, and the second term is the arithmetical intensity of the code multiplied by the memory bandwidth. And then I told you that you can compute optimal arithmetical intensity for any device, where you take the theoretical peak flop rate and divide that with the theoretical memory bandwidth. And if you would plug this number into the previous formula, you will end up basically just taking minimum out of peak flop rate and peak flop rate. So in that case, the performance will be a peak flop rate. And then if you take a code where the arithmetical intensity is smaller than the optimal arithmetical intensity, then you will end up evaluating this term, and that is always guaranteed to be smaller than peak flop rate. And this would very well agree with the earlier observations where we had this XPy code that has a very low arithmetical intensity, and therefore this is going to evaluate to be smaller than peak flop rate. And in case of other code where the arithmetical intensity is larger, we will end up evaluating this function as peak flop rate. And then we could go and look through different optimal arithmetical intensities. And for this desktop CPU, we will get a number of 5.7 flops per byte. For the 14-core Xeon one, we will get a number of around 12 flops per byte. And for the V100, we will get a figure of 7.7 flops per byte. And if we now plug these numbers, which is computed on the previous graph, we can see that all three platforms will land between these two clusters, indicating that GEM, neural networks, and bottleneck codes are compute bounds, and FFT, sparse vector multiplication, stencil codes, and XPy are going to be compute bound codes. And one key thing to understand is that the arithmetical intensity will be different when you're doing a different precision, because you will end up dividing with the fewer number of bytes being moved. So for single precision, we will get the number 11.4 for the desktop CPU. For the Xeon, we will get 24, and V100 we get 15.6 flops per byte. And again, everything ends up shifting to the right, because it is not only the optimal arithmetical intensity of the device that will change, it is also the arithmetical intensity of the code that's being considered. And if you go to half precision, then if you use the numbers given by NVIDIA, the V100 has arithmetical intensity of 124. And in this case, actually, this jumps so far that now even some GEM operations might become memory bound, but deep neural network operations at least some of them are going to stay compute bound. At this point, we could plot these two numbers on the same graph. So on the horizontal axis, we still have arithmetical intensity, note the logarithmic scale. And on the vertical axis, I have put the flop rate. And again, we are using the logarithmic scale here. And we put here the Skylake, and then we look at the corresponding theoretical peak flop rate of the device. And then we can go and add more information to this graph. So we can take this function we found earlier, where we take the minimum out of peak flop rate, and then we have arithmetical intensity times the memory bandwidth. This side of this function is going to be simply evaluated as a flat line to the right of the optimal arithmetical intensity of the device. And on this side, we will get a slope where the slope will depend on the memory bandwidth of the device being considered. And as already mentioned, everything on this side is going to be memory bound, and everything to this side, on the right side, is going to be considered compute bound. And now if we go and take this arithmetical intensity for the AX operation, that was 1/16. It is going to be here on the extreme left corner. And then we are going to plot a line here. And to the line, we will actually then plot the flop rate that we actually measured for each one of the devices. In this case, you can actually see that when we use this model that would give the prediction, the actual flop rate we have measured is very close to the theoretical number that we had just computed. Then if we do the same operation for the gem kernel, this time the arithmetical intensity is around 32. So we will get the vertical line here. And then we plot the actual flop rate for each device. And this time, again, we note that our prediction would agree very well with the actual measurement we did. The only exception is the one for the Xeon CPU, for which the reason is very likely related to the BLAS library I'm using, that is not using the full instruction set of the CPU. And now briefly going back to this Xeon kernel that I earlier mentioned, that the naive implementation doesn't necessarily perform very well. Instead, you have to use a well-implemented implementation. And I mentioned that the arithmetical intensity you get for the naive implementation is around 1/88. And then I told you that the real number is around 32. So why is this? So the thing is that if you go and implement this matrix vector multiplication for each element in the product matrix, you will end up evaluating this dot product formula here. And this will give you this number of flops per byte. However, if you instead take the matrices and divide them into submatrices like this, now you can use this formula to evaluate a block in the product matrix. So instead of having a sum where you're multiplying together the scalars, here you have a sum where you are multiplying together matrices, adding them together. And these, in the end, these will end up computing exactly the same result. It is just that this function is a scalar manner, we are multiplying scalars, and this works in a blocked manner, we are multiplying matrices together. The neat trick here is that as long as we make the matrices A, I, K, and B, J, K, J small enough, we can actually fit them inside the CPU cache or the shared memory in SMP. And this means that all the threads that belong to the same thread block can go and load this data together and store it into the shared memory. And the end result is that this operation, individual submatrix multiplication, can be performed with a really minimal number of data transfers from the global memory. And since the arithmetical intensity is going to take account only the memory transfers from and to the global memory, it means that the denominator in the formula will decrease, the arithmetical intensity will go up, implying that based on the Roofline model, we should get the higher performance, because in the figures I showed earlier, the vertical line should move closer to the right, therefore indicating a higher performance. And this is just a visualization of what is happening when we are doing the scalar multiplication. Each thread that is running on the CUDA core has to go and load all the data by itself on the memory. Of course, there is going to be the cache here between, but it doesn't actually help that much because each thread is still operating independently. There is no cooperation between threads. But in this blocked variant where we are doing multiplying these submatrices together, we can go and download these submatrices, the shared memory. And it is going to be all the threads in the thread box joined together, thus getting a very high memory bandwidth. And then it's all in the shared memory. And now the threads can move together and pull the data from the shared memory that will have much higher memory bandwidth than the global memory. And then when we move on the next block, they will be pulled again at very high bandwidth from the global memory, and then pulled even higher memory bandwidth from the shared memory. Then the last topic to mention is the PCIe bandwidth that I have been completely ignoring at this point. So in the earlier codes where I had this AX kernel being executed, what I did that I started the timer just before I launched the kernel. Then I waited for the threads to finish with the CUDA device synchronize. After that, I stopped the timer. And in this way, I got 47 gigaflops of computing power, and I got the memory bandwidth to 756 out of a theoretical 900. But if we go and modify this code in such a way that we actually put the memory transfers between these timers, that is the only change we do. Earlier, the memory transfer was up here, hidden. We pull it here and pull the other memory transfer again here. So we are, in addition to measuring the kernel runtime, we are also measuring the data transfer from the host through the PCIe connect to the global memory and back. And when we run this code, we note that this time I'm getting only 0.3 gigaflops out of the card. And the memory throughput is going to be only 5 gigabytes per second out of 900. So clearly, it will have a huge effect when you start and stop the timing. And more importantly, this will, in a real world, also affect your performance. So in case of the AX kernel, clearly you don't want to be a situation where you're just moving the data from the host memory to the GPU, doing the calculation and moving it back. You actually want to keep the data on the GPU memory as much as possible. And that is exactly what's happening if we are in a situation where the data is already in global memory. You are pulling it through the memory controllers in the GPU itself with the bandwidth of 900 gigabytes per second. But if instead the data is in the host memory, now all the data has to go through the PCIe line that has a bandwidth of 16 gigabytes in either direction, theoretical possible of 32, and only then you get the 900 gigabytes per second. But this doesn't help at all because it is the PCIe connection that is going to form the bottleneck, the performance of the code. So if we would go back to the Roofline model where we had the performance equals minimum out of peak flop rate times arithmetical intensity times the memory bandwidth, if we replace the bandwidth, global memory bandwidth with the bandwidth of the PCIe, then we will of course get a different Roofline model. So on the right side of the optimal arithmetical intensity, that is around 200, we will still get the peak performance. But to the left of it, that is now everything below around 200, we will get way lower performance. And in this case, to the various reasons I will discuss during the afternoon, you can see that we are not actually nowhere near what is predicted by this model. So the model will change depending on where you put the data. If the data is already in global memory, you will get this model that implies that you get very high performance as long as the arithmetical intensity of your code is reasonably high. But if you have to pull the data across the PCIe connect, then the arithmetical intensity has to be really high in order for you to get the peak performance. And now I'm coming to the end of the presentation. So what I have here is that I have two hands-ons under the hands-on/3 modeling. The first one is called one.compare, and here you will given two codes. Yes, we have a question.
If our CUDA-based implementation also includes code in CPU, at what point do we need to measure time? How do calculate compare performance?
In general, if you want to be fair and you are saying that you are reporting how fast your code is, you should start. In general, if you want to be fair, then you should, and you are telling some person who's using your code that if you put your data here, call my code, and this is how fast it's going to run. Then you should start the timer around the same time where you think that the user will start using your code. And you should stop the timer around the time when you think your user has stopped using it. So in case of the XPy kernel, and you're marketing it to people that, oh, you just have your data in the in your computer, and I will do it this fast, and then you're showing the measurement, assumes that the data is already in the GPU memory, then that would be kind of unfair. So I think you should include pretty much everything that is expected to happen when you're running the code in a normal situation. Okay, I got complimented by my lecturer. Thank you. So going back to hands-ons, the first hands-on is that you basically take these two codes I have shown during this lecture, and you will pretty much do the same analysis to the code I have shown you during this lecture, and then you will see if your results agree with the ones I have shown during this lecture. And the second one is actually where you take the code you have worked yesterday afternoon, and you do some analysis with them. In the instructions, I'm telling you that you are comparing the starting point code, my solution, and your own. If you did not have time to do all the hands-ons yesterday, you can simply compare the starting point against my model solution. And again, the solutions for these hands-ons can be found under solutions/3-point modeling.